Welcome, everyone. So my name is Michel Gomens, and I'm the department head in mathematics. And I'd like to welcome all of you to the department for these 2025 Simons Lectures in Mathematics, given by Maryna Viazovska from EPFL, l'École Polytechnique Fédérale de Lausanne, where she holds the chair in number theory. So the Simons Lecture is our most prestigious lecture series in the department. It was created about 25 years ago by a generous gift from Jim and Marilyn Simons, and you are all aware of the philanthropy of the Simons Foundation and Jim and Marilyn Simons. In fact, we are in the Simons building. There are a bunch of Simons professors in the audience. There are Simons fellows, Simons investigators, and so on in the building. We have had some amazing speakers in the past, and this year is no exception. So Maryna was born in Kiev, Ukraine, and studied both in Ukraine and in Germany, getting her doctorate from the University of Bonn. She's maybe a number theorist, but and an expert in modular forms and L functions, but her work has really transcended into other fields of mathematics. And our most celebrated result is, of course, the fact that E8, the E8 lattice provides the densest packing of spheres in 8 dimensions. And then also the extension with others in the room to the Leech lattice in 24 dimensions. And so this result was cleverly constructing a magic function using L functions and based on the work of Cohn and Elkies before. So for these set of results, she received the Fields Medal in 2022. She's the second woman to be awarded a Fields Medal. Heartfelt congratulations. And she has also received many other prizes. The list is very long. I'll get started, but I'll have to stop before the end. The Salem Prize, the Sastra Ramanujan Prize, a Clay Research Award, the Fermat Prize, a New Horizons Prize, and so on. So in addition to our impressive research accomplishments, it's also impressive to see that Maryna is a leading administrative figure. So she has been the chair of the math department at EPFL. At MIT, they choose the least accomplished person. There they use the most accomplished person. So, and a year ago, she was the founder of ICMU, the International Center for Mathematics in Ukraine. To provide mathematical activities and stimulation because of, in response to all the suffering that the Ukraine people and scientists have endured because of the Russia's invasion into Ukraine. She's now the scientific director of that center. And in fact, we have a representative in the department, Pavel Ettingov of that scientific committee, but unfortunately couldn't be here today. But you came to listen to her, not to me, so please warmly welcome Maryna.
Michael, thank you very much for the introduction. So it's a great pleasure to be here and to give the series of lectures. And so all my 3 lectures will be about the sphere packing, as I find it a very fascinating subject. And so the first lecture would be about upper bounds, about how good the sphere packings cannot be. So, and so here Michael already told you that I will speak about magic functions and what they have to do with the upper bound for sphere packings and how to construct them. And then I plan that for my two other lectures, I will speak about lower bounds, about how good sphere packings can be. And so here it seems that now is the moment, and new results appear like every 2 years. So it's, yeah. And before that, it was maybe like every decade or every century. So it's, yes, this seems like an exciting moment for lower bounds for sphere packing. But so for today's lecture, so let me speak about the magic functions. And so, yeah, so let me start a little bit from far away. So, yes, so one of the areas of mathematics that I love a lot are the geometric optimization problems. And of course, geometric optimization problems, this is a very wide class of questions. And but here are the kind of questions that I thought about at some point or that I find interesting. So for example, the various types of packing problems, or they are somehow the various types of covering problems. And it turns out that both these types of problems, they're also closely related to finding optimizing Laplace spectra, or to finding shortest geodesics on manifolds with certain geometric constraints. So, and for all these types of optimization problems, there is a common framework from a common set of tricks or methods that helps us to get a partial result, but sometimes even the complete resolution of the problem. And so today the focus would be mostly on the packing problems. So, and what the packing problem is. So we fix a metric space. In this metric space, we have a notion of the distance, of course, but also what would be, we'll need some kind of notion of volume in this metric space would be useful for us. And then the question we can ask ourselves is how many balls of a given radius can be contained in a metric space. And then again, there is a wide class of questions which can be put into this category. So maybe some most famous are the sphere packing in Euclidean space, or the theory of error correcting codes, or finding independence numbers in a graph. So all of these questions, they can be phrased as a certain packing problems in a suitable metric space. And so these problems, they are known to be hard, and they're also known to be important for various applications. And so another somehow related set of problems, maybe, so the way I would see it as some kind of a weighted packing problem or relaxed packing problem would be to minimizing potential energy for the configuration of points again in the metric space. So we have our metric space, we choose points in there, but now we imagine that our points, they interact with a certain potential, and so, and this potential depends only on the distance. And then the question would be to if we fix the number of points, or if we fix the density of points, we would like to find these configurations with minimal possible energy. And then, of course, so what this has to do with a packing problem, for a packing problem, we can think of this energy potential being, for example, infinity if 2 points are too close together, and 0 if they are farther away. Then this would be, this way we could see how packing problem is a partial case or limiting case of such a problem. And so again, problems of this type, they're known to be difficult, and we don't have a general method how to solve all of them, or how to, for example, how to obtain sharp results to show that certain configurations are optimal. At the same time, there is a type of optimization problems that we know really a lot about, and this is linear optimization. And so here you can see a classical problem of linear optimization is that we have we have a cone, and in this cone we would like to optimize, for example, value of a linear functional. And so these are very well-studied problems. They also, unfortunately, they are also hard. But here we have many algorithms. We have a very nice duality theory for this type of optimization problems. And so this is somehow one of the main. So the duality is one of the main ways to find sharp solutions to the optimization problems. And so now one of the, ways which was established is that we have this nonlinear difficult packing problem or energy minimization problem. And one of the things we can do, we can reduce it to a linear optimization problem. So this is something which is typically done. So of course, what I'm telling now, maybe this is a bit of old news. So linear optimization is not the only exciting type of optimization. There is also a semi-definite optimization, which is maybe more modern and also can be done quite effectively. But in my story, it will be all about linear optimization. So the idea is to take this nonlinear optimization problem and reduce it to a linear one. Of course, as we are doing so, we might lose something. There is no guarantee that the new problem has the same solution as the old one, but at least we will get some estimate. And so the way to linearize this energy minimization problems is the following, is by considering the so-called cone of copositive functions. So what is a copositive function? So let M be our metric space, and then we would say that a function from the support of the metric on this space to the complex numbers is copositive if the following double sum is always real and non-negative for all finite subsets of M. And so, of course, the definition of copositive functions, it will depend on our metric space. And so here there is another class of functions, which is a bigger one, so-called positive definite functions. And so here actually not bigger, it's a smaller one. Sorry. So a smaller class of functions is the class of positive definite functions. So here the condition is stronger. So here this double sum, in double sum we are introducing the weights assigned to each point. And so now such a weighted double sum has to be non-negative for all finite subsets and for all possible complex weights that we assign to the points. And so, of course, just it follows from the definition that positive definite functions, they are all copositive functions. And so now here a typical situation which happens, so I will maybe formulate it not in a very formal way, but usually this cone of copositive functions is a very difficult cone. And so for many interesting metric spaces, it's even known that somehow it doesn't, we don't have an effective description of copositive functions, and if we had it, then we would solve many problems that are believed to be difficult. So this cone of copositive functions, it's a difficult one. At the same time, for many interesting matrix spaces, the cone of positive definite functions is actually simple, and we can work with it. And so there's now here the strategy for solving packing problems or this energy problems becomes the following. So reduce the problem to an optimization problem in the cone of positive definite functions. And of course, this is a relaxation, so the sharp result is not guaranteed anymore. However, this is how we can make estimates, and in many cases, those estimates, they're actually very interesting, and it would be difficult to obtain them by other methods. And sometimes, in some situations, like in situations I'm going to speak about today, even despite this relaxation, we can still solve some interesting optimization problems. And so, yeah, so here is for example, a theorem which is maybe a very simple version of how this of how the energy problem can be linearized. Okay, so suppose that there exists there exists a copositive function such that the value of this function at 0 is 1, and the value of the function at every distance bigger than fixed distance r0 is smaller or equal than this -1 divided by n minus 1. Then we would know that any r0 code in this metric space, or any packing of balls of radius r0 divided by 2, it can contain at most capital N points. So this maybe would be a nice theorem which we can apply to some compact metric spaces. So for example, you can think as a possible application here would be a coding theory in Hamming space. And so here's a very short proof. So suppose that such a function, so f exists, and suppose that x is an R0 code, so it would be a set of points inside of M, so such that the distance between any two distinct points is bigger or equal than R0. Then we know that the function f is a copositive function. We know that such a double sum has to be non-negative. And at the same time, we also know that our function f satisfies these special conditions. And so we can rewrite this double sum in the following way. We will separately write sum of pairs which lie at the diagonal, where two elements in the pair are equal, and the sum over pairs of non-equal points. And now we see that because x is an R0 code, it means that so first, for equal points, we know that the distance between equal points is 0. So this first term will be just equal to the size of our set x. On the other hand, we know that for each term at the second sum, it will be this negative, smaller or equal than this negative number. And so we can estimate our sum in this way. But at the same time, we know that this number is bigger or equal than 0 and smaller or equal than this expression, which involves the size of x. And from here, we can deduce that the size of x cannot be bigger than n. And so for example, so one of the historical uses of this theorem which I showed you was the Lizard's proof of the optimality of Hamming code. So this is a Hamming code. It's a binary code of length 8 and dimension 4. And here in gray, you can see the generating matrix of this code. And so the minimal distance of Hamming code is 4. And the number of elements in the Hamming code is 16. So now it turns out that this method, rather simple method which I showed before, if it's applied to this code, it can show that the Hamming code is an optimal one. So this is a... And so to apply our method to the Hamming space, we have to understand what are the positive definite functions on this Hamming space f2 to the power n. And so here what I can show you is that, okay, so we can take, so here what really plays an important role here is that Hamming space has a lot of symmetries. It is an abelian group. And so what comes to save us is the Fourier analysis. So here first we can see this function fy of x, which is just a, so to say, harmonic wave going through our Hamming space. And so here x dot y, it's a scalar a product of two vectors. And so now if we take any sum like this, here if we fix y and take sum over pairs x1, x2, which are elements of any subset x of the Hamming space, what we will get, we will see that this double sum, in fact, can be rewritten as a square of the absolute value of such a single sum. And so this sum is always, of course, therefore such a double sum will be always non-negative. And okay, at the moment, this does not really satisfy my theorem. And this is because this function fy, it depends somehow on an element in my space, not on the distance to anything, like on distance to 0. But we can somehow make a little, what we can do here, we can, for example, now if we are averaging this harmonic wave, for example, over all elements y of the same Hamming length, then what we will get, again, by the symmetries, we will get a function which will depend only on the Hamming distance from x to 0. And we can construct our function which depends only on the distance of between points as this averaged harmonic wave applied to the difference of 2 points. And so actually it's so if we do the averaging, we know that the result would be expressed in terms of the what is called the Kravchuk polynomial of the which depends on the dimension, length of x and length of y. And so here's the following theorem, which again goes back to 1970s. It tells us that if x is a code is a code inside of is a code of length, binary code of length 8, and it has distance 4, then the number of elements in this code will be smaller or equal than 16. And so how is it done? It is done by constructing an explicit positive definite function. So namely the function f is defined as this this sum of Kravchuk polynomials. And as we've seen before, Kravchuk polynomials, they are positive definite, so the sum of Kravchuk polynomials with positive coefficients also will be positive definite. And so,
question,
yes?
Maryna. So the Kravchuk polynomials generate all the set of positive definite.
Yes, I think yes, and this is a theorem. This is a Schoneberger theorem, and it works not only for Hamming space, but there is a more general somehow theory for like essentially for spaces that have a lot of symmetries. And so now, as in my talk, I would like to speak about sphere packings in Euclidean space. So here is the adaptation of this theorem that I showed you before to the Euclidean space. And so this is a result which appeared in a paper of Kohn and Elkis, but then independently a similar result was discovered by Dmitry Gorbachev. And so both results, they were published in 2000s. Yeah, so I think the paper of Kohn and Elkis is from 2003, and the dissertation of Gorbachev is from 2006. But then, of course, they're always before preprints, and yeah, so just not. And so this, so maybe like let me tell you like what is a bit, of course, why Euclidean space needs special adaptation. So what is technically more difficult about Euclidean space, it is that the total volume of the space is infinite. And so it somehow one really needs to think how to adapt the theorem from the previous slide, because previous theorem it worked nicely for compact spaces, but here we need some to find a better formulation. And so here it turns out that in Euclidean space the property of being positive definite is captured by the sign of the Fourier transform of the function. So essentially one can say that functions which are positive definite in Euclidean space are essentially the functions with a positive Fourier transform. Of course, again, here one has to be careful because Fourier transforms don't exist for all the functions, so there should be some maybe caution about what to do with functions which don't have well-defined Fourier transform. But for us, actually, for us to obtain our result, it's sufficient to work only with Schwarz functions, so with functions which have fast decay. And so maybe one more remark I would like to say that the original paper of Kohn and Elkis, it is about it was not only for Schwarz functions, but for a wider class of functions. So here maybe requiring for function to be Schwarz, it's a bit of an overkill, but this works later in my application, so I just want to simplify my life a little bit. So suppose that, so the theorem is the following. So suppose that we have a function f, which is a Schwarz function, and it means that the function and all of its, so the function is infinitely smooth, and all of its derivatives decay faster than any inverse power of a polynomial. And suppose that our function is non-positive outside of a ball of radius r0, and its Fourier transform is non-negative at all Euclidean space, and also we normalize our function in its Fourier transform so that the value of the function at 0 and that the value of its Fourier transform at 0 is 1. And then if we can find such a function, then we know that each periodic configuration of points in Euclidean space such that the distance between any two distinct points is at least r0 would have density at most 1. So here again what I'm hiding a little bit, so I do not define what is a, okay, no, I think it's okay. So here I speak about periodic configurations, and then what is the density of periodic configuration is more or less clear. It's just the number of points per volume in a fundamental, and we can take it in a fundamental domain. And then, of course, if we know this statement for periodic configurations, we can also make it work for reasonable non-periodic configurations. And so now let's denote by delta d the sphere packing constant in dimension d, which is the density of the densest sphere packing in the Euclidean space Rd. And so here is a table of the known upper bounds and no densities for small dimensions from 1 to 36. And so here you can see the red line, it's an upper bound, and this upper bound comes from the previous theorem. So these are the upper bounds obtained by Kohn-Elkis linear programming method. And the blue line, this is the best known density in each dimensions, and then of course, this should be a discrete, because we have a discrete set of dimensions, so this is, in fact, a discrete set of values, but then I connect them by line just to improve the visibility of the plot. And so if we look at this plot, so there are a few things we can see. Okay, first is that when d is big, it seems that the gap between two bounds is kind of growing and growing and growing. So here what I told you, that indeed this method of linearization, it's a nice method, but then probably it does not tell us all the truth about the sphere packing problem. On the other hand, the other remarkable thing here is that in some points, actually two lines coincide, or visually coincide, numerically coincide. And so we can see that there is this coincidence in dimensions 8 and 24. But then something which is not very visible on this plot is that they also coincide in dimension 1 and 2. But then the sphere packing problem in dimensions 1 and 2 is maybe not so interesting, even though the fact that two lines coincide is quite interesting. Anyways, and so in the 2003 paper, Kohn and Elkis, they have really observed that the numerical bounds in dimensions 8 and 24, they come very closely to the densities of the E8 lattice and the densities of the Leech lattice. And so this is the result I would like to speak about today, is that actually the proof that these two bounds, they indeed coincide. And so here are some facts about the E8 lattice and Leech lattice. So these are somehow remarkable geometric and combinatorial objects. They appear in many different areas of mathematics. Probably if you have not heard of them from my talk, maybe you learned about them from some other place. And so E8 is the unique even unimodular lattice in the Euclidean space of dimension 8, where even means that the lenses, the squared lenses of all vectors of this lattice, they are all even integers. And unimodular means that the co-volume of this lattice is 1. So we have, roughly speaking, 1 point per unit of volume. And of course, it also, for example, it can be constructed as the root lattice of the E8 root system. And we know that the shortest non-zero vector in E8 has length square root of 2. And so there are 240 such shortest vectors. And interesting fact is that those shortest vectors, they also form they provide a kissing configuration, so the best possible kissing configuration in dimension 8. And so then if we scale our lattice properly, we can construct sphere packing by placing a ball at a ball with a center at each point of the E8 lattice and choosing the radius so that it will be the length of the shortest vector divided by 2. And so then if we want to normalize our lattice so that its covolume is 1, then the radius should be 1 over square root of 2. And so the theorem I would like to speak about today is that the E8 lattice is universally optimal. Oh, sorry. Okay, so first that the E8 lattice is the best, provides the best sphere packing in dimension 8. And so another result I would like to talk about today is that the E8 lattice is universally optimal. So it means that it's optimal not only for the packing problem, but also for for a family of energy optimization problems. So it's optimal for any Gaussian, real Gaussian energy between points. And so Leech lattice is a lattice also with somehow similar properties. And so here we know that in dimension 24, there are 24 even unimodular lattices up to an isomorphism. And only one of them has shortest vector of length 2. So of course, if we speak about even lattice, then smallest possible length is square root of 2. But here, like among these 24, there is one which does not have any vectors of length square root of 2, but has the shortest vector of length 2. And so the Leech lattice was discovered in 1967, and its construction actually came from coding theory. And if you want to learn about more constructions for the Leech lattice, you can refer to the Conway's books. And I think in his book, he gives like 24 different constructions of Leech lattice. So it seems like whatever you're trying to construct, you will always construct Leech lattice at the end. So, and so there are many of them, like many of them are algebraic, coming from different areas of algebra. And so what is also interesting that the number of shortest vectors of Leech lattice is quite big. So it is this 6-digit number. And those vectors, they also provide the kissing configuration in dimension 24. And it's actually known that it is this configuration is the best and it is unique. And yeah, so this is also known actually for quite a long time. So it was simultaneously proven that the kissing number was simultaneously found for dimensions 8 and 24, and it was found by the same method. And the method is, again, the method I showed you before. It was this method of linear programming, which in this case gives just the perfect result. And so we can also consider the lattice packing associated to the Leech lattice. And so here it's very convenient. So we don't, if you want to have to take a volume of our covolume of our lattice to be 1, then we can take balls of radius 1, which is also beautiful somehow. And so this is somehow the natural normalization in. And so working together with Henry Kohn, Abhinav Kumar, Steven Miller, and Denishil Radchenko, we have proven that the Leech lattice is the best sphere packing in dimension 24. And then the Leech lattice, it also has this property of being universally optimal. So it's optimal not only for the packing problem, but also for the problem of finding configurations with minimal Gaussian energy. And so the solution of the problem for dimension 8 was to find explicitly this function which satisfies the properties of the Kohn-Elkies theorem. And so this is what I'm going to speak about today, is to show you how to construct this function. And then similarly for the Leech lattice, also this time working together with Steven, Abhinav, Henry, Danilo, and Danilo, we have constructed a magic function which, so radials for Schwarz function, which satisfies all the conditions of Kohn-Elkies theorem for dimension 24. And so as I remember, this terminology, it was coming from Steven Miller, who suggested naming the functions which somehow provide us with sharp results, to calling them magic functions. And so here is the plot of the function. This is how the function looked like. So this is the plot of the magic function which proves the optimality of E8 lattice. And so here it's, because this is a Schwarz function, so it has rather fast decay. So to make it a bit, to look a bit more interesting, I've normalized it and multiplied by this exponential function. So the rate by which I multiplied it is a bit arbitrary. Here, this is just to see better the profile of the function. And so what we can see here, okay, so we can, if we look at this magic function, what we can observe is that it has a lot of zeros and double zeros. And those double zeros, they are exactly at the points which is the spectrum of our lattice, which are the lenses of vectors of our lattice. So on my plot, they are lengths squared, but again, I've done this for aesthetical reasons to have equally spaced zeros on the picture. And so this fact that the function, the magic function and its Fourier transform has all these double zeros, it's not a coincidence. Actually, this is a consequence of satisfying the Cohn-Elkis conditions and also the existence of E8 lattice. And so this is sometimes in a linear, so in optimization, this is what is called complementary slackness. So if we are searching for an optimal solution, then we can expect this optimal solution to satisfy a number of linear constraints. And so here, these double zeros, they actually give us a clue on how to find the magic functions. Okay, so first, here is this, again, like the proof that both the magic functions, they need to have well, the double zeros which we have seen on the plot. And so here, this is how the story works. So, okay, so here let lambda be any of the two lattices, either E8 or the Leech lattice. So then if we compute, we know that the value of our function at 0, it is bigger or equal than the lattice sum of this function. And this is because we know because the function satisfies the Cohn-Elkis condition, and Cohn-Elkis condition on a function is that if the length of a vector is big enough, then the value of the function has to be non-negative. And so here we are applying the Poisson summation formula. And so after we applied the Poisson summation formula, we know that the sum of the values of Poisson of Fourier transform over the dual of our lattice will be bigger or equal than the value at 0. And this is because because of the function satisfies Cohn-Elkis conditions, and the Cohn-Elkis conditions on the Fourier side is that the values of the Fourier transform are non-negative. So we can throw away all of them except for one, and we will get an inequality. And then we know that the value of Fourier transform at 0 is 1, because this is our normalization. And so now we can see that all these inequalities can be true only in the following case. It can be true if the function and then its the values of the function and the values of the Fourier transform have to vanish at all non-zero vectors of the lattice. Also in this case, somehow we know that, because we are both speaking about E8 lattice and Leech lattice, that in fact the lattice is equal to its dual. So the second order of vanishing is also something we get again from the combination of these equalities and the Cohn-Elkis conditions. Okay, and so now how to construct the function. Okay, so now the function, it turns out that the function can be constructed in the following way. So it can be given as an explicit contour integral. And so, the chicken-claw contour will be used to prove that such a function indeed satisfies all the conditions of the Cohn-Elkis theorem. And so here we will define our function in the following way. So it would be a sine square times the integral, and here f lambda is a holomorphic function, and it will it's supposed to have nice transformation properties at the upper half plane. So it will be a function which is defined at the upper half plane, and it has nice transformation properties under the group of linear fractional transformations. And we also want this integral to converge if r is bigger than the length of the minimal vector in the lattice. Okay, so so this is how the transform to. So now what we have to do, we have to first make sure that we have this sign squared which guarantees our zeros, and this is how we do it. We do it in a following way. So we take our function and write it as a sum of three shifted integrals, and now what we do, we make a somehow changing these three contours into one. So this is the chicken claw contour. Okay, so we can. So now what is the advantage? So here I like this presentation of a function came somehow out of nowhere, and later in the lecture I will actually explain a little bit where it came from. But now it's kind of a wild guess, and so I try to convince you that like this, actually this form of the function is well compatible with what we know about the function, what we know about the double zeros, and also double zeros for the Fourier transform. So first, if our function is written in such a way, then it will be easy for us to compute its Fourier transform. And so here what I do, because my function is constructed as a contour integral of a Gaussian with a complex coefficient, with a complex parameter z. So here z, it's a number in the upper half plane. And so we know how to compute Fourier transforms of Gaussians. And so this way, formally, this would be the Fourier transform of the function I have defined. And so now what we would like to somehow to do to guarantee that such a contour integral will also have these double zeros. So here somehow I want to really, so now I have my function written as this sum of three integrals over vertical lines, and now I would like kind of to go back from here to there and get again the sine squared. Yeah, so now before I can do it, I will have to do some computations with contour integrals, changing, for example, to change the variable. So here I hope you trust me that I've done it correctly. And so this is what I will get at the end. And so here at the end, I'm going to play my last card, is that because what I've written before, I told you that my function phi, it is some function defined on the upper half plane. It is holomorphic. It satisfies some nice transformation properties. And at this step, I will actually impose transformation properties on phi. And of course, we'll hope that such a function does exist and does what I wanted to do. And so now it turns out that these are actually, if I think about all the conditions, everything I want to have from my function, it turns out that this in red, this would be the conditions I will get. And it turns out that I am lucky, and these conditions actually, they can be, these equations, they can be solved explicitly. And so if I can solve these functional equations for phi, then my three contour integrals will come back into this sine squared times one contour integral. And so now the final step, of course, and this is what I have constructed so far, I have constructed a function which satisfies vanishing conditions which are compatible with the Kornelkes theorem, and same vanishing conditions are satisfied for the Fourier side. And now the final step, of course, the actually, if you go back to the Kohn-Elkis theorem, what we need are not the vanishing conditions, but are the inequalities. So now I need to check that the function satisfies inequalities. So in a sense, I've imposed all these conditions of phi, and with my assumptions, I could get only one reasonable function. And now the final test is to see, okay, so does it satisfy the inequalities? And so the very final step is to see that this function indeed satisfies the inequalities of the Kohn-Elkis theorem. And fortunately for me, this function did satisfy this inequality. So the function itself, it could be written explicitly in terms of modular forms. And because it was a very explicit function, it was possible to verify the inequalities actually by analyzing the expression under the integral. And so now we can do similar things for the universal optimality. And so now let me introduce what is the universal optimality. Okay, so first in this long and technical slide, I define what is the energy of pairwise interactions for a configuration of points in Euclidean space. So here, of course, as we're speaking about Euclidean space, it's not interesting to speak about a finite set of points. It's interesting to speak about infinite set of points which has a well-defined density. You can think of like points in a crystal, or maybe in some molecules and some very big bodies. So we want to think of it as being big enough, and then we want to normalize somehow to go away from infinities. What we would like to do, we will compute the average energy per one particle. And so this is the quantity we would like to minimize. And of course, the well-posed problem would be like this. So suppose that we consider all these configurations of points with a fixed density rho. Then we are searching for a configuration of fixed density with the smallest possible energy. And because if we don't fix density, our solution could be somehow like very, very sparse, or on the other hand, very, very, very condensed set of points. And so now we would say that discrete set of density rho is universally optimal if it minimizes p energy whenever p is a completely monotonic function of squared distance, or easier way to say it, if it is minimizes p energy for any Gaussian like this. So for any function which is a Gaussian with any positive real parameter alpha. And in fact, all completely monotonic functions of squared distance, they're all linear combinations of such Gaussians. Or like, not linear, but like convex combinations. And so this is the theorem we proved together with Henry Kohn, Abhinav Kumar, Stephen Miller, and Danilo Radchenko, is that the lattices E8 and the Leech lattice are universally optimal. And so here again, the method for proving this is the linear programming. And so here is the linear programming method, which is adapted for energy minimization problem in Euclidean space. So this is a theorem by Henry Kohn and Abhinav Kumar, and it tells us, so let P be our energy profile, and suppose that we can construct an auxiliary function f, such that f is a Schwarz function, and f is bigger or equal than p for all non-zero x, and also the Fourier transform of f is bigger or equal than 0, then for every subset of Euclidean dimensional space of density rho, its lower p energy will be at least this number. And so again, this is a relaxation of the energy minimization problem, and in general, there is no reason for this bound to be sharp. However, for this case of optimization of Gaussian potentials in 8-dimensional and 24-dimensional space, it turns out that actually this method gives the optimal result. And so here again we can use this idea of complementary slackness to get extra information about auxiliary function f. If we assume that such a function exists and it does provide a sharp bound, then this function would have to satisfy also a number of conditions. For example, the values of function would have to satisfy with the values of the energy profile at all non-zero lattice points. And the Fourier transform of f has to vanish at all non-zero lattice points of the dual lattice. And also all these equalities, they will hold to the second order. And so it turns out that this information is in fact sufficient to recover the function. And so in order to show this, we have proven the Fourier interpolation formula. And the formula says us the following. This is also from the joint work with Henry, Abhinav, Stephen, and Danilo. So we have proven this formula for dimensions 8 and 24 because this was what our application needed, but it can be proven actually in any dimension. So the only difference would be that here we have these two numbers d, which is the dimension, and n0 is the point where we need to start sampling our function. And of course, as dimension is bigger, we can start sampling later. So we need somehow can postpone some of the shortest points. And so it tells us that if we have a radial Schwarz function f, and we know all of the values of the function at all square roots of even positive integers and the values of its derivative. And of course, here I speak when I say f of square root of n, it means that f evaluated at all vectors of the length square root of n. So here's a bit of using this bit like abuse of notation because it's a radial function. Of course, it depends only on the length of the vector. And so we know the same information for its on the Fourier side, then we can actually recover the function. And so since this formula, we have actually recently some other Fourier interpolation formulas have been proven. So as a preparation for this 2019 result, we have proven simple Fourier interpolation formula. So not here, this is a second order interpolation formula. We're interpolating function from the values of function and its derivatives. And to prepare for it, together with Danilo, we have constructed a Fourier interpolation formula which interpolates only from the values of function, but not at the square roots of even integers, but at the square roots of all integers. And then actually there is also, so here is a small list of other related results. So it turns out that on one hand, there is nothing so much special about square root of n, and if other sequence has the same density properties, then also there will be a Fourier interpolation formula associated to these nodes. But then there are also other types of like interesting Fourier interpolation formulas, for example, coming from the zeros of zeta function. But this might be included mostly for the destruction. And so now, if you know the Fourier interpolation, so now we can actually can maybe explain you a little bit again, like where this modular forms condition is coming from. So because in the packing problem, it seems like a guess, but maybe this actually solving this problem helps to explain where the guess is coming from. And so now we would see that. Okay, so first is that if we do have this magic function, Then from the complementary slackness, we would know that our magic function would have to look like this. So the magic function, of course, it will depend on the energy profile P. And so by the Fourier interpolation formula, this is how it will look like. Because we know everything what happens on the side of x, of f of x, but then on everything from the Fourier side, it will just vanish. Because there all the values of f Fourier have to vanish. And yeah, so now if we know the functions En and Bn, then we are in principle done. So we just, if you do know En and Bn, the last step would be just to prove these inequalities. And so now the final step would be how to find these numbers, the functions En, Bn, the interpolating basis. And so we can find it in a following way. So we can arrange this interpolation basis into a generating function. And but now if we think of the interpolation formula for the complex Gaussian, we would see that it is in fact equivalent to the following functional equation for this generating function. And so now by solving this functional equation, we can find the generating function f, and therefore find also the basis an, bn, an tilde, and bn tilde. And so this equation, again, so this equation, it is a functional equation where the group of the SL to z acts on the function f, as we think of f as a function defined on the upper half plane for a variable tau which lives at the upper half plane. And so this would be, in fact, the complete, somehow, also a bit of a hidden information about the function f is that we have this first equation which comes from the interpolation formula applied to the Gaussian, but other two equations, they come from periodicity, and this periodicity is built into the generating function itself, just because it's defined as such a series. So this series, they're just defined to have this double periodicity property, or being linear periodic. And so now it turns out that this function, it can be solved explicitly in terms of, and so this function capital F will have an integral representation. And so then the final step is actually to prove these inequalities for this explicit function f. And so then these inequalities, they already imply the inequalities from the Kuhn-Kummer theorem and prove universal optimality of E8 lattice and Leech lattice. So thank you very much.
Any questions? And if you have a question, you should take the microphone. It's being recorded.
Really great talk, thank you. I was just curious if there's some sort of like rigidity or stability result known in dimensions 8 and 24.
Actually, there is a paper of I think João Ramos and Danila Radchenko where they do establish stability result, and actually the stability result, it does use also the magic function to show the stability.
Thank you.
Any other questions?
For sphere packing, this argument seemed to be tight for dimensions 1, 2, 8, 24. For this sort of universal optimality, what does the situation look like in, say, dimension 2?
Yeah, so there also it seems like it should work numerically, but analytically, actually, dimension 2 seems to be, at least for this method, it seems to be more challenging than 8 and 24, which is a bit strange, but yeah. Yeah, then maybe like the reason as I see it, like why things don't like work so easily, is that if we think of the lenses of vectors, so in dimension 2, of course, the candidate is the A2 lattice. But if you think of the lenses of its vectors, they have more complicated structure than, they're not just like square roots of integers. It's like lacunary sequence, which is a bit interesting. And so this, and also it could happen, I don't know, since maybe now it's a bit more like a speculation. So here it seems that in this case, if these magic functions, they are unique, at least if we search for magic function in a reasonably good space. And in dimension 2, I'm not so convinced. So maybe one of the reasons why dimension 2 is more difficult is that because there is like not one but many magic functions, and it's difficult to choose one out of them.
Maryna, thank you for the beautiful talk. I have a question. So if you're given some magic functions given by explicit formulas, but involving integrals, it's a big lengthy expression, how one can check that this function is non-negative somewhere?
Yeah, so of course, yes, how we have done it, we have actually like written down an argument, but it was, okay, so I think now in my original paper, this argument of checking that, so the function which I had to check, so maybe I can show you, okay, so here, so I did not do it for the integral. So in our cases, we were quite lucky, and we could just analyze, for example, we were writing here an integral and want to show that this function, for example, is negative. But then the expression under the integral already was negative. So integral did not contribute that much. And the expression on the integral, it was a very explicit function. So like some combination of modular forms of small weight. So in a sense, like if with a suitable change of coordinates, it could be expressed, I think, in terms of like polynomials of like variables of two variables on a square, logarithms, and elliptic integrals. So those are, and then it was somehow just so some kind of brutal force argument how to, then there was a numerical aspect to it to show that, okay, this is like this very explicit function, we have this bound on its derivative, and then we have computed it on this small grid, and so therefore it has to be positive. So like, for example, here it's like, because the function for like on, so for example, at the like boundary of this square, we could have like a separate argument just computing the asymptotics, but in the middle it was somehow computing it on a fine grid. But since then there was actually an improvement, and now for at least for dimension 8, there is actually like a mathematical proof which says like which does not include any use of computer. So I think it's done by Dan Romnik. He has done it in dimension 8. And there is another student, and I think it's, I'm not sure if it's already published or not yet, but he have actually found a nice argument which works for both E8 and Leech lattice. But then it's somehow, but it's again proving inequality. So like this, this modular form has positive coefficients, therefore it has to be positive. Or this, now I like take a polynomial of it which has no roots, therefore it also has to be positive. So it can be broken into those like smaller steps, but yeah, like analysis. You know?
Thank you.
Let's take one more question.
Thank you. So if I recall correctly, the Cohen and Kumar 2007 paper is on the sphere, and you stated the result for configurations on the Euclidean space, and I was wondering if it's easy to go from the sphere to the Euclidean.
Okay, that theorem is actually stated for Euclidean space.
Okay.
So, yeah, so Henry maybe can correct me if I'm wrong, but that theorem it is for Euclidean space, so I did not have to do anything. So.
The last section of the paper is for Euclidean. Just repeating what Henry just said. So let's thank Maryna again. And